continuous improvement tools may include many tools. One of the important tool we call statistical process control, or SPC. In statistical process control, we will discuss the use of control chart to detect changes in the process. We will discuss about the variation of output. We will discuss about variable charts. We will discuss about attribute charts. We will discuss about sampling and sampling distribution. Okay, in normal distribution, the sampling distribution will follow the normal distribution curve. In normal distribution curve, the center of the curve will be mean, which is x bar, and the spread of the curve we call standard deviation, or sigma. Range is the difference between the largest observation and the smallest observation into the sample size. This picture tells the differences between the standard deviation of the process and the standard deviation of the sample. Okay, as you can see that from this picture, that standard deviation of the process is quite large, because the process includes all population, which has far more many compared to the sample. The sample may have only quite a few specimens or items, thus cause the distribution of sample narrows in variation than the process distribution. The relationship between the distribution of the population and distribution of sample is distribution of sample, or sigma x equal sigma divided by square root n, when n is sample size. In process, variation happens commonly. Variation is something that causes the outcome to change a little bit. If you look closely to the product or services that you produce from the process, you will see that they are no two items alike. Some variations are good, some variations are bad. The good variation we call common causes variation. Okay, common causes of variation is a variation that happens randomly. It is unavoidable because it is a source of nature that make us different, that make the outcome different. Okay, common causes variation. Common causes of variation. If you draw the distribution, the distribution will follow normal distribution curve, which the mean will be center, and the curve look like a bell curve with symmetry on the left and right. Assignable causes of variation, on the other hand, it is a variation that caused by something else, not ordinary. It can be identified and detected and eliminated. Assignable causes of variation, when it happens, it changes the distribution of the outcome. It may change the mean, the spread, or the shape of the distribution. we will use statistical process control to detect assignable causes of variation. This picture shows the effects of assignable causes of variation. The purple one, okay, is the process with assignable causes that drive the process to change the mean. Assignable causes may change the distribution curve into a more to add more variation, or it's also change the size or the shape of the curve to add a symmetry and from left and right of the curve. When there are assignable causes of variation, it must be detected and eliminated, because assignable causes cause poor processes, which lead to poor product and services. Control charts are tools that can be used to detect assignable causes of variation. The control chart may include 3 components: mean, which is the center line, upper control limit UCL, lower control limit LCL. In order to construct control limit, first you must randomly select samples, and this sample will come from the process. You must plot the outcome of the sample. If there is a sign of assignable causes, you must eliminate them and repeat the process. Okay, this picture we will use this to complete the case study. This flowchart tells the process of statistical process control. First, you start out by collecting samples. Recommended sample size will be about 25 to 30, at least 20. Once you collect samples, you record the data on the table, compute control limit, draw a control chart and plot. If there is a sign of assignable causes, then next process is going to be the box at the bottom. Spatial causes of variation are sought for out of control conditions, and the out of control points are removed. New trial center limit and control limit are computed for the remaining point. The remaining point are then plot the new chart. So this process will be experimented. Use some Excel table, and then you go back. If there is no assignable causes, then you go to use the outcome as your new control limit. Okay, so this picture show you a sample of sample distribution. The first 2 samples, the outcome tend to be within the control limit. We call in control. The third outcome, on the other hand, there are some occasions that the process produce the out of control limit. In this condition, we can summarize that the process is not in control or is out of control. When the process is out of control, it implies that the process has assignable causes. We must eliminate it root cause of the problem in order to prevent this from happening in the future. Okay, this picture shows a normal situation when the outcome is in the limit. No action is necessary. Okay, this one is still in limit, but we call run because the outcome tend to be closer to the lower control limit. This one we call sudden change. Need to be monitored because the outcome tend to be widely range. This one we call exceeds control limit or out of control. At least 2 occasions, we need to take action. Okay, I'll talk about that later. Okay, to construct a control limit, there are 2 types of control limit. The first control limit we call control chart for variable. We call control chart for variable because this type of control chart can be used to measure something, can be used to plot or to detect something that has varies number, can be used to describe something that can be measured. Like for example of variable chart can be height, weight, length, distance, something that can be measured. The first chart for a variable chart we call an R chart. R stands for range. Upper control limit are equivalent D4 R bar. R bar stands for average of range. Lower control limit are equal D3 R bar. D4 and D3 are constant that provide 3 standard deviations. Okay, as you can see from organization may adopt many set of standard. And one set of standard that normally adopted by organization we call 3 Sigma standard. 3 Sigma standard is equivalent to about 99.3% effectiveness or about 0.6% poor quality. This table gave you an easy to use indexes for manager in industry to find upper control and lower control limit. That's 3 Sigma standard, sometimes we call industrial standard as well. Okay, this is additional table which includes index for D2. Additional table which different sample size on the left. There. If you have higher sample size, you can use this table. Okay, another type of control charts for variable we call X bar chart. Okay, the purpose of X bar chart is to compare mean. On the other hand, the purpose of the R chart is to compare the variation of outcome. The X bar chart, upper control limits equal X bar or X double bar plus A2 R bar. Lower control limit equal X double bar or X bar minus A2 R bar. when X double bar is an overall average of the past sample means. A2 is a 3 sigma constant. Okay, now let's look at this example. This example shows how to compute range and X bar. Okay. Range is the maximum minus the minimum number of in the sample. Okay, in this case you can see there are 5 samples. Each sample has 4 observations. Thus sample size is 4 or n equal 4. The average is the average of each sample, which is the sum of all observations in one sample divided by 4. Overall average is R bar, which is the average of all 5 samples. X double bar or X bar bar also is an overall average of X bar. To conduct upper control limit and lower control limit, we must know D4 and D3. From table 5, okay, when sample equal 4, okay, R bar D3 is 0, R bar D4 is 2.282. When you go back, you substitute that to get upper control limit R and lower control limit R. Okay, R bar can be used for the center line or the nominal. Then you plot R for each sample against upper and lower and nominal. You can see that for this chart there is no out of control point. To compute X bar, you use the sum of observation of each sample divided by sample size. To construct the upper and lower control limit for X bar, you find A2 from the table and you find out, and you plot against the plot the X bar for each sample. X bar will be a nominal point. From this slide you can see that the last observation is out of control. Therefore, with these two occasions, we can summarize that the process is out of control. Okay, so with this knowledge we are going to go back to a sample. On your sample, you can see that it also show you how to find upper and lower control for each X bar and R chart. And also I also show you how to estimate the process standard deviation by using the formula R bar divided by D2. When D2 come from table that available, make sure that you use the right sample size. Okay, so we are going to maybe experiment this on example number 2 together. So I'm gonna go to slide. On your slide you can see there's a 3 sigma table, D2 table. Okay, so we are going to add one more key. We're gonna call it this one example 2. it. Okay, on example 2, a Vicky car watch has target average of, so we call X bar 390 second. Okay, we have a sample size N of a 9 car. We have R bar average range of 10 second. Okay, so when N equals 9 sample size, we're going to go back to find out when N equals 9 what should be the D4 and okay, you can see when okay, A2 0.337. Okay, now let's go back. D3 is 0.184. Okay, and D4 is 1.816. Okay, and then we're gonna find D2 also. Okay, and on D2 we're gonna go back to the slide to find out where the D2 is. Okay, D2 is 2.970. Okay, so we're gonna construct upper control limit X, lower control limit X, upper control limit R, lower control limit R, and we also gonna find out sigma. Okay, sorry for the interruption. Sigma process. So we're gonna find out for upper control limit X bar equal X bar plus A2 times R bar. Okay, lower control limit X bar equal X bar minus A2 times R bar. For the R, upper control limit R equal D4 times R bar. Lower control limit equal D3 times R bar. Okay, and sigma equal R bar divided by D2. Okay, let me check D2 again. Okay, D2 is 2.97, that's correct. Okay, now don't forget to save it. Okay, so with this example, you can also use that to apply for example 3. I hope you give that a try. Okay, on example 4, we have a raw data like that. Example 4 does not have X bar and R bar available. So in this example, you must create columns for first for the arm, another one called X bar. Okay, for the R we are going to use function R. We're going to use function max minus min function. X bar, we're gonna use function called an average. Okay, so we're gonna, for all, we're gonna use function called max, and then you highlight sample. Okay, minus min, then you highlight sample. Okay, and then you can apply that, drag it down to the rest. For X bar, you can use function called average, and then you highlight for observation. Okay, and then for the overall average for the R bar, we can also use average function. Okay, and then you can also apply that. Okay, so we call that X R bar or X bar bar. Okay, so once you have X bar bar and R bar, then also it is important to identify your sample size. Okay, in this sample size, in sample size. Sample size in this case will be 4. Now, so this is the most important thing that you're gonna do. Sample is a sample size, because identify wrong sample size will identify wrong parameter. Okay, so for this example, you have 6 samples. Each sample you pick 4 observations to measure. So the sample size is 4. Okay, when sample size is 4, then you go back to the table to find out A2 is 0.729. D3 okay, D3 will be 0, D4 will be 2.282. And D2 will be 2.059. Okay, so we are going to trying to construct the control limit. Okay, first we're gonna do X bar chart by upper control limit X bar, lower control limit X bar, center line X bar, and X bar. For the R chart, sometimes we use the dash to separate them, like that. R chart, we are going to find upper control limit R, lower control limit R, control limit R, and the R. For upper control limit X bar, okay, please review the formula again on your first page. Upper control limit X bar equal, Okay, x bar bar. Okay, don't forget to hit function 4 to freeze the amount, plus a2 function 4 times r bar function 4. Okay, so you use function 4 to freeze the amount. Okay, now let me make a note. Function 4 is on your keyboard on the top is to freeze. Okay, so you drag it down. Lower control limit equal x bar bar function 4 minus a2 function 4 times r bar function 4. Okay, the center limit will be the r bar function 4. X bar will be the x bar on the left, which is the plot that you're gonna make. Okay, for upper control limit, r equal d4 function 4 times r bar function 4. Lower control limit equal d3 r bar function 4 times r bar function 4. Center limit equal r bar function 4. Okay, r is also on the left. Do not freeze it because you want the plot to change. Okay, with these 4, sometimes you can also maybe create some type of box table. Okay, the first X bar chart, you highlight all 4 columns, click insert, click line chart, click any plot. Okay, with this chart you also select the one that show the title and like this one, not that one. Okay, we don't need to show all that. Like that, and change the top part to maybe X bar chart. Okay. For the R, you highlight for that in third line, or you can choose on this one. You can also choose maybe that one called R chart. Okay, up to you which one you would prefer. Okay, based on the look of these 2 charts, you can see that the process from the both chart, the process is in control. Okay, I hope students practice this on example available to you on the Excel sheet. Students have example 5 data to practice.